Okay, so we are on Unit 3, and the topic is memory management. We will cover the following learning outcomes: explain memory management, describe the principal requirements for memory management, explain reasons for memory partitioning, list and explain the various techniques, okay, for memory management, and then define paging and segmentation. Now, we spoke about the different functions that an operating system plays in the computer. And one of those functions was memory management. It's something that is very complex that happens behind the scenes. You don't see it as an end user. So we want to discuss and drill down on some of these concepts that form part of memory management. So we say memory management is the process of allocating primary memory to user programs. What do we mean by primary? We mean main memory, or another term for it as well as RAM. So you need to get used to all of these terms because they get used interchangeably. Reclaiming that memory when it's no longer needed, protecting each user's program memory area from other user programs. For example, ensuring that each program only references memory locations that have been allocated to it. Okay, the memory manager is responsible for the maintenance of free space, free memory blocks. Okay, so the operating system must constantly give allocations, take away allocations where a program is no longer using them. It needs to also be able to protect processes from each other. Okay, and we want to talk about all of these components. So the key thing is that we're able to remember, and you can see in this slide that we're supposed to remember what we mean by a process. What is a process? What do you mean by process? So a process is any program that's in execution. Okay, so any program that's awaiting execution, we refer to it as a process. And these processes obviously go from a hard disk or hard drive into main memory, where they're now waiting for the CPU to be able to execute them as instructions. Okay. And we know how this happens, obviously, through the instruction cycle, which we said was the fetching and stuff like that, the whole instruction cycle. That's how it gets executed by the CPU. Okay, so a process is defined as an entity which represents the basic unit of work to be implemented in the system. When a program is loaded into the memory and it becomes a process, it can be divided into 4 sections: the stack, the data, the program, and the process control block. Don't confuse these 4 sections of the process to the instruction cycle, okay? 2 different things. What I'm saying here is that when a program itself is sent to the main memory, it can be divided into these main components, okay? So we have the stack, and the stack contains information about the perimeters, okay? The code, functions, methods, all of the code in that particular software. And then the data component contains information about what kind of variables were defined, okay? We have global variables and then we have static variables. So what kind of variables were defined in that particular software? And then we also have the program, which contains information about how much space allocation is required for this process, okay? The program component. Then we have the process control block component. And this component is very important because it contains critical information about the process itself. Whenever a program is opened up on a computer, it is assigned a process ID. It's a unique ID that is used to reference that particular process. So the process control block is the portion or the component of a process or a section of the process that contains information about the number 1, the process ID, and number 2, and I'll focus on only these 2. There's other pieces. If you research further, you'll see that there's other information that is stored within this process control block. But the two main ones is the process ID, which is a unique number to identify the process, and the process state. What is the state of the process? It can either be active or it can be idle. Okay, and there's a reason why I'm focusing on those two, and later on in the presentation, I'll tell you why. So there are certain requirements that need to be met by the OS in order to implement memory management. So in order to manage memory effectively, the OS must have memory allocation policies, okay? Methods to track the status of memory locations, so it should be able to track in the main memory what are the allocated frames, what are the free frames, okay? Policies for preempting memory from one process to allocate to another. Okay, so it also has to be able to clean the memory and free up space for any urgent processes. So those are some of the requirements in order to implement memory management, and the operating system has to be able to do this. So some of the key terms that are used in this topic or this study unit: a frame, a page, and a segment. So what do these terms mean? So a frame is a fixed block length of memory. So we take the memory and we divide it into equal parts, and we refer to those parts as frames. Okay, you can see here on the little diagram on the left-hand side of the screen that there is actually a graphical representation of how memory would look like. Okay, it's a conceptualized version, not how it actually looks in the real world. But the key thing to take out of this is you can see the operating system. In the previous lecture, we referred to it as the resident monitor, but you can see that the operating system takes up its own portion of the memory. So you never get the full capacity of your own memory. If you have 4 gigs in your computer, you never get the full 4 gigs because a certain portion of that 4 gig is reserved by the operating system. So what happens to the remaining part of the RAM? It means the remaining part is then referred to as the user program area, which is the area at which the programs can now sort of divide and use for themselves. And so we refer to them as frames. So you take the user program area of the main memory, you divide it into equal frames. Hence, you refer to it as a fixed length. Okay, it's a fixed length block because they're of equal size. And then when it comes to pages, what are pages? Pages are fixed length block of data that resides in secondary memory, such as a disk with the K, okay? A program of data may be temporarily be copied into a frame of main memory. So as much as we take main memory, we divide it into equal size fixed length block frames. We also do the same for processes that are awaiting execution. So you take a program, maybe you want to open up a web browser to browse the internet. Okay, so when you click on that web browser, it becomes a process. So in terms of pages, that process will be divided into equal parts. And those equal parts of the process are sent to the RAM and obviously are assigned frames. Now it's not as straightforward as I'm saying it. There are complications because you can see here, assuming that this is a RAM and it's been divided into 6 frames. What happens if the process is 8 frames? What happens if the process is divided in, if the process is divided into 8 pages or 10 pages and we only have 6 frames? So it's not always as straightforward as I'm saying it. It's not always going to be 6 frames and 6 pages. Okay, because remember, the pages are on the process side. It's the process divided into fixed length block of data. And also we have segments. Okay, and they say with the segment, it is a variable block of data. Okay, it is a variable block of data that resides in secondary memory. An entire segment may temporarily be copied into available region of main memory, referred to as segmentation, or the segment may be divided into pages which can be individually copied into main memory. So segments are a bit of a challenge because just like the pages, it's a division of the process, but it's a division of a process into variable blocks, not fixed blocks, which means they're not going to be, the divisions are not going to be of equal size with segmentation. Okay, and it's very tricky. However, even with systems that use segmentation, those segments can be further divided into now fixed length variable blocks, which are known as pages. Okay, and I'll just scroll to the next slide so that you see a diagram of how segmentation would look like. So considering what we saw in the slide, which was speaking about the process and how a process is divided into different sections. So in terms of segmentation, we can send different sections of a program to the main memory. That is a variable block because you can see yourself that the sections are of different sizes, the different lengths. These are not equal sized length. Okay, which means there'll be equal size capacity. Unlike if you are using paging, where all the pages that are sent from the hard drive into the main memory will be of equal size. But it doesn't mean just because we have segmentation, we cannot have paging within segmentation. Because what could happen then is we can, as much as we can segment a program before it's sent into main memory, but we can segment it and then page it again so that each section of, or each segment of this particular program is sent in pages. Okay, so at the same time, as much as there is segmentation, but there's also a more efficient way of implementing segmentation, because segmentation is very risky when you're sending a variable block of sections of a program, and there's no guarantee that it'll fit. Not that there's guarantee if we were using pages, but pages reduce the amount of space taken up by a program in the main memory. So paging is somewhat of when the RAM is under pressure, it may turn your segmentation back into paging. So that's basically what I'm saying. When it's under pressure, it may need to turn your segmentation back into pages. Okay, so this is a logical view of segmentation. A program, which is a process which is divided into different sections, and it's in variable blocks, and it may be sent as segments rather than pages to the main memory. So we tend to refer to as logical versus physical address space, or real memory versus virtual memory. Those are the terms we normally use in memory management. So the concept of a logical address space that is bound to a separate physical address space is central to proper memory management. So logical addresses are generated by the CPU. We also refer to them as virtual addresses. They are created by the CPU, and the CPU then goes and borrows additional memory from secondary memory when it's under pressure. So we refer to those as logical or virtual address spaces. And then we also have physical addresses. This is what you actually physically, it's there. It's in the RAM. It's a physical chip, which means when you open up the computer, it's a physical component that has those address spaces. So that will be the significant difference between logical address spaces and physical address spaces. Logical address spaces, we can say they are created at runtime or borrowed by the CPU from the hard disk. Then we have the concept of contiguous allocation. Okay, so we said a process, when you launch a process on a computer, you open up a program, it's divided into pages. Forget segmentation for now. It's divided into pages of equal size. And also the frames as well. on the RAM's side are divided into equal size frames. Now, contiguous allocation means that the pages that go from secondary memory into main memory were allocated to adjacent frames. They were allocated into adjacent frames, which means if I say to you there were 5 pages that the process was divided into, it means page 1 went into frame 1, page 2 went into frame 2, page 3 went into frame 3, and so forth up until frame 5. Those are contiguous allocation of space. In the perfect world, that's how it will be. But what normally happens is that 5 pages, those 5 pages, you send the first 3. By the time you want to send the 4th, another program has already allocated something here into this 4th frame. So now it has to skip. Now it has to use this 5-page process has to now use frame 5 and frame 6. So then it means your process, that 5-page process, would basically be would be what we refer to it as non-contiguous spaces, non-adjacent spaces. Also, if a process is able to fit into one frame perfectly, then that's fine. That's a contiguous space. Okay, so contiguous spaces means that the process is assigned to adjacent partitions of the RAM, or it's assigned to one particular holistic frame where everything fits into that one frame. So then we have memory management policies. Okay, I'm open to questions. So because I only see you once a week, if you have a question on a particular slide, I'm open to questions. You can. I can't see your hands here, but if you feel like you want to unmute yourself and ask a question, you're more than welcome to do so, and I'll answer. Or if you need clarity on a particular concept. So also we said there are these memory management policies that we expect out of operating system to have efficient or effective memory management. Okay, and so these are relocation, protection, sharing, logical organization, and physical organization. So we're just going to go one by one and talk about these different policies. So the first one is relocation. Relocation is the process of adjusting program addresses to match the actual physical addresses where the program resides when it executes. Okay? Why is it needed? Well, you have this RAM again with 6 frames, and those 6 frames are shared between different programs on the computer. Okay, so when a particular program is no longer using a particular frame, it means it can be taken out. It can be taken out from that frame and sent back to its original location. But this is also not done permanently. It's done on a temporary basis because the program is idling, which means the end user is not using it at the moment. Myself on my computer, I'm on PowerPoint, I'm on Teams, but I have other programs that are open in the background and they are minimized, which means those processes would go into an idle state. And there's no reason why they should be there while they're in idle state in my main memory on my computer. So they'll go into an idle state and they'll be sent back on a temporary basis to the secondary disk, but there's no guarantee that when they return, they will be placed back into the original frame that they were taken out of. Okay, so why is it needed? Why is relocation needed? It's needed because you don't want to tie programmers with restrictions to say your program must only use up this much of RAM or this much of memory. Okay, so you don't want programmers to have restrictions when they're writing code. It doesn't matter which other software is going to be open while your software is open. The people that build Photoshop and the people that build Visual Studio, it doesn't matter. They don't really care if Photoshop is going to be running while Visual Studio is running. They don't have to worry about that because there's proper memory management in the operating system, and the operating systems have the capabilities to relocate idle processes. Picture a game. A game is on a computer is something that takes up so much of memory. Maybe some games even take up to like 4 gigabytes or whatever, 8 gigabytes of space for themselves. So when you're launching and playing that game, in the background, your other information is idling. Okay, it's idling. Your other programs are idling, which means they can be replaced on that RAM. And then when the game is closed, then those programs are returned back. So there's a specific term that we tend to use to define this process of relocation. We call it swapping. Active processes need to be able to be swapped in and out of main memory in order to maximize processor utilization. Specifying that the process must be placed in the same memory region when it is swapped back in would be limiting. Consequently, it must be possible to adjust addresses whenever a program is loaded. Okay, so you would see relocation or swapping in a multi-programmed operating system. Okay, it doesn't matter in a uni-programmed operating system because there is only one program or process there at one given particular time in the user area of the memory. And you can see in the slide in front of you now how this concept of swap in and swap out actually works. So we have process 1, which was using up all this user space in the main memory. And then we have process 2. So process 1 has gone idle. Assuming it's gone idle, it will be swapped out of this area. And assuming this backing store component defines the secondary storage. So process 2 will be swapped in and can start using that space. So this is just a diagram of how this concept will work. Okay, so apart from relocation, we also have protection. And protection is a requirement for memory management. Why? Because we don't want these processes to cross-reference each other. There's a security risk. Only processes with permissions to cross-reference each other can do so within once they're in the main memory together. We don't want one process accessing data from another process within the memory during execution. Okay, so there's protection, there's independence between these processes unless there's permission that is granted by the OS. Okay, so that is a very important security feature put in place. However, it doesn't mean just because there's protection that processes cannot share data. They just have to share in a controlled manner with the right permissions in place. Okay, so there is, for example, multiple processes may use the same system file, and it is natural to load one copy of the file in main memory and let it be shared by those processes. It is the task of memory management to allow controlled access to the shared areas of main memory without compromising protection. Okay, so when they say without compromising protection, it means the shared file that these two processes are sharing would still meet certain permissions, read or write permissions. So we are saying it's more efficient to have two processes sharing the same system file as opposed to opening up a new instance of the system file for each of the processes. It's more efficient to do it that way. So we allow for sharing, but it needs to be in a controlled manner where maybe we only put in read permissions for that system file for all of these processes sharing it so that no other process is able to delete that system file while the other processes are reading from it. Okay, so sharing, it's a very important part, but it has to also be protected and protected without compromising protection. And also there is logical organization. And what they are saying here is that although main memory is structured in a very one-dimensional linear manner, okay, you can see here in the diagram, the conceptual diagram for main memory, that it's very one-dimensional. It's just boring frames, okay, it's one-dimensional. But programs are not necessarily organized this way. Programs are, you look at a program as one thing, but it actually contains multiple things, modules. Okay, it actually contains modules, and these modules form part of the logical organization of the program. Okay, and the modules can work independently in terms of allowing certain read or write permissions. Okay, so you can enforce your protection in your program at a module level. Okay, so logical organization is very crucial in memory management because it allows us to enforce protection of our software at different modules. So if you don't want certain parts of your program shared with another process, so you can protect it per module with whatever module is housing sensitive data. You can protect that module independently or individually, rather. So that's the benefits of having that logical organization within your memory management policies. And then we have physical organization, and physical organization speaks to the fact that there is physical two-level memory of a program storage, which is physically the disk or the hard drive, and also physically the RAM. And they say that disk is slow and cheaper because it was made to accommodate bigger capacity or space, so it's going to be slower. And then RAM is faster and more expensive. Okay, so that's the physical organization in the computer must be that way. You must have RAM, you must have disk storage in order to implement good memory management policies. Users should not have to be responsible for organizing movement of code or data between the two levels. So you are not responsible for that. It's something that happens behind the scenes through the operating system. Okay, and then there are also these two terms: fragmentation, external fragmentation, and internal fragmentation. So external fragmentation, total memory space exists to satisfy a request, but it is not contiguous. Okay, well, I told you in the earlier slide what contiguous is. Contiguous spaces, not residing in one location and also not residing in adjacent locations. It splits between non-adjacent locations. So hence we refer to it as non-contiguous, which is how we get external fragmentation. And internal fragmentation, allocated memory may be slightly larger than requested memory. This size difference is memory internal to a partition, but not being used. I just want to move to the next slide where you see the diagrams of this fragmentation so it makes better sense to you. So we're saying we have internal fragmentation when a process is assigned to a frame that is bigger than what it actually needs. So you can see the gray portions. Okay, the gray portions is the wasted space. It's wasted because the fragments that was taken up is not taking up the full assigned space capacity. Okay, so we have wasted space within that one frame, and that term is referred to as internal fragmentation. So external fragmentation occurs when there is enough space in the memory to run a process, but that space is in non-contiguous frames. Okay, and you can even say internal fragmentation leads to this problem of external fragmentation, because now we have you can see we might have free space, fragment. We might have enough capacity to run a process, but it's not going to be within residing or adjacent frames within the main memory. So it leads to external fragmentation, external wasted space. And this one, internal fragmentation, you can see it as internally wasted space. And then we also have dynamic loading. So there is no need for any process or any program to send all of its pages all at once to the RAM. Okay, it's I refer to it as hoarding or hogging the memory when the computer does that. But dynamic loading means that it's fine, send all the pages that are required for execution now, so that when other pages are needed later on, they are requested. They are loaded on request. So it doesn't mean just because the process is 6 pages and there are 6 frames available that you need to send everything. No, you can send the first 2 maybe if you feel like the first 2 are enough to run the program, and then when the next 2 are required, then the next 2 are fetched from the secondary memory. So that is, we refer to that as dynamic loading. Okay, so, and these are the different techniques that we find in memory management. We have fixed partitioning, where a memory is divided into equal size partition, fixed length partitions. Okay, what are the strengths of this? Simple to implement, little operating systems overhead required. What are the weaknesses? Inefficient use of memory due to internal fragmentation. Okay, and I'll return to the slide just now, but if you see here, they have a diagram of a fixed partition memory, and we have fixed partitions where all of the partitions, all of the frames are 8 megs. So what could go wrong here? Okay, fixed partitioning, you will experience here and there internal fragmentation, where a page or an entire process is sent into a frame, but it doesn't necessarily need all of the 8 megs. So it leads to internal fragmentation. So that's one of the weaknesses of using this fixed partitioning. Then we have dynamic partitioning, which means a process or a page will partition the main memory dynamically based on the amounts that it needs. Okay, but then you can see in this slide that this process slowly becomes free for all. Okay, the processes are just taking as how they want. And what does that lead to? It leads to external fragmentation, because now if here in this diagram D, maybe process 1 now times out. Okay, it times out or it's idle. So now we have 24 megs of space left, but you can see there are non-contiguous frames. So this space cannot be used efficiently because it's not a process. If it's placed on this, it's not going to be in adjacent frames. Okay, so that leads to what? Dynamic partitioning is good, but at the same time, it could lead to external fragmentation. That's one of the disadvantages for it. And then, so its strength, we said there's no internal fragmentation because a page would have created a partition that it needs. So there's no internally wasted space, but external fragmentation would exist at a later stage. Simple paging, main memory is divided into a number of equal size frames. Each process is divided into a number of equal size pages of the same length as frames. The process is loaded by loading all its pages into available, but not necessarily contiguous frames. Okay, simple paging uses the method of fixed partitioning. We have the RAM is divided into 6 frames. We have the process is divided into equal size pages as the frames. Okay, that is simple paging, which we spoke about earlier. Simple segmentation as well. Each process is divided into a number of segments. A process is loaded by loading all of its segments into dynamic partitions. that need not to be contiguous. Okay, so with simple paging and simple segmentation, there is no dynamic loading, which means when a process is paged, you send everything to the frames. The only time pages will be left behind if the RAM doesn't have a choice because it doesn't have enough frames to accommodate the other frames. So it's going to leave behind, and then the concepts of virtual memory will kick in. So simple paging, that's how it works. We divide it into simple pages, we divide into equal size frames, and then we send the stuff there to the main memory. Simple segmentation, we divide them into what? Into segments. And then we send all the segments into the main memory, and dynamic partitioning happens, which means we don't have fixed frames, but we create partitions dynamically based on the sizes of the segment. Okay, and we said this could lead to external fragmentation whenever there's dynamic partitioning of the main memory. And then the last two, how do they differ? Okay, so we have virtual memory paging and virtual memory segmentation. With virtual memory paging, it means that we do not send to the main memory all the frames. We just send 1 and 2, and the concept of dynamic loading applies. So when we need the rest of the pages, then we send them dynamically. Same thing applies with virtual memory segmentation. It means although the software or the program or the process was segmented at the hard disk level, but we did not send everything at the same time to the main memory. Instead, we sent what was needed at that particular time, and all the other remaining segments are sent at a later stage. Okay, so these are the different techniques. They're very much related, as you can see. You can find fixed partitioning in paging and dynamic partitioning in simple segmentation and so forth. Then we have placement algorithms. Okay, so there are certain algorithms that are used to decide where certain processes or pages are allocated within the RAM. I just want to find a clip for you. Hopefully, I'll be able to locate it still. Okay, so I'm hoping this will play without any issues. I may need to reshare my screen to enable the sound. Just a quick clip to show you how this actually works visually.
Memory, assigning portions called blocks to various running programs.
Can you guys confirm if you can hear the sound?
Yes, sir.
You can hear the sound, okay. So yeah. I just want you to just look at, before I talk about the placement algorithms, just look at the animation, because in terms of animation, you can see how this works, how the different placement algorithms work.
To optimize overall, however, we will only cover two of them. That is, to allocate the jobs in memory. However, we will only cover two of them. That is first fit and best fit. What is first fit allocation? It is technique that allocate the first hold, that is big enough for job. The search will start at the beginning of the memory. The advantage using first fit is faster in making allocation. In contrast, a disadvantage leads to memory waste. What is best fit allocation? It is similar to first fit, except the search starts at the last hole allocated. Different from first fit, best fit memory allocation makes the best use of memory space, but slower in making allocation. So, let's get one example of first fit allocation in fixed partition. We have 5 memory blocks in our memory. First one is 10K size, second one is 5K, third block is 30K, fourth block is 25K, last block 40K. We have 4 jobs. Job 1, Job 2, Job 3 and Job 4. Job 1 have 20K job size, Job 2 have 15K, Job 3 have 30K and the last one, Job 4 have 5K job size. Let's try to allocate Job 1 into memory block. Job 1 cannot fit into block 1 with only 10K size, so we will move to block 2. Job 1 also cannot fit in block 2 with only 5K size. In block 3, we have 30K size so we can fit our job to this block. In first fit, we don't have to check remaining block after we find block that can be allocated. After we allocate Job 1 into block.
Okay, so if you pay attention to what happened there, we took a page from assuming secondary memory, which is job 1, and we sent it into the main memory. And what this algorithm did, this algorithm is called first fit. It scans the RAM until it finds a frame that is big enough. And the reason why they call it the first fit is because it would literally assign a job or a page an allocation which it finds first, the first one which fits. And you can see it registered the first 2 because they're not big enough in terms of capacity compared to the space required by the job. But when it reached the third one, the third frame was 30K, the job is 20K, it can fit. But what happens? We have 10K internal fragmentation, space wasted. So what you can say about this algorithm, there is a good side to it and there is a bad side to it. The good side to it is that it's gonna definitely allocate a partition faster for the job, but it's inefficient because it's wasting space. Okay, so that's one benefit. It has an advantage and it has a disadvantage. Disadvantage is that it leads to internal fragmentation. Sometimes, by luck, the first one that fits is going to be of equal capacity. The first frame is going to be equal in size to the job, but that's not how it mostly happens most of the time, okay?
We will have 10K internal fragmentation. Next, we will quick go through remaining jobs.
Okay, so same things will apply to the remaining jobs. It will do the same thing. First fit, now that this one has been taken by job 1, which means the next one it can send job 2, which is greater capacity, equal or greater capacity is 25K. So it can only send it here. I just wanna, for the sake of time, I just wanna move to the best fit algorithm. Okay, so this is how the best fit algorithm will work.
Job 1 will try to allocate into memory block 1. Job 1 cannot fit into memory block 1, so move to block 2. Job 1 also cannot fit into memory block 2, so we will try to block 3. Job 1 can fit into block 3 but need to try all of memory block, so move to block 4. Job 1 also can fit into block 4. Block 3 is bigger than block 4, so block 3 now the best one. Job 1 also can allocate into block 5 but it is bigger than block 4. So, the best one still block 4. We select block 4 as the best fit for job 1. So, next.
Okay, so in terms of the best fit algorithm, there will be literally a scan of the entire memory, which is one disadvantage about the best fit algorithm, is that it scans the entire memory. So allocations are not going to happen as fast as the first fit algorithm. However, the amount of space that is lost due to internal fragmentation will be less. Okay, because you can see here, this is less than what it would have wasted if it ended up here in terms of the first fit algorithm. Okay, so there are pros and cons to both allocation algorithms. And okay, so there is best fit, first fit. Don't worry too much about the worst fit method. which finds the largest block on its list so that the remaining part is large enough to be used in later requests. The way that blocks are organized on the list determines how fast the search for an available block succeeds or fails. Okay, so the two main popular ones are first fit and best fit, and you saw according to that animation how it actually works. Okay, and paging we already talked about. So paging and frames, two concepts that are very much related. When we have equal frames, fixed frames, we also need equal sized pages, but not all the pages are sent at the same time. A paging table is what we find in a computer, and this paging table resides on a component we call the memory management unit. The paging table is there to map the pages to the corresponding frames. Okay, so if a process can only send 3 of its pages to the RAM at a particular time, it means the other content will be sent later. It will be dynamically loaded. So the mapping table is the one that's keeping track which pages have already been sent and which pages still need to be sent, and which frames those pages that were sent already are residing in. Okay, so there is a paging table and it contains all of that information. It's mapping these two fixed block of memory together. Okay, and then so this memory management unit is actually a physical chip on the hard drive, but don't worry about it too much now. In the next lecture, when we talk about virtual memory, that we're drilling down on how actually this virtualization of memory actually works. We want to speak about this memory management unit component more in detail. Okay, so in conclusion, we covered memory management, and we said it's one of the most complex tasks that have to be done by an operating systems. Needs to be treated as a resource to be allocated to and shared among a number of active processes. So active processes, not idle processes, active processes need to share this resource together, and various initiatives are taken by the operating system with the aid of the CPU to make this happen. Desirable to maintain as many processes in main memory as possible. Desirable to free programmers from size restrictions in program development. Basic tools are paging and segmentation, and it's possible to combine the two. When segmentation is failing, it will default to paging. So segmentation itself can end up being paging and end up being converted to paging. So paging, small fixed sized pages. Segmentation, we have pieces of varying size or variable blocks of data. Okay, so that concludes our lecture for today on memory management. Okay, so we still have maybe like 4 minutes left before the lecture ends, so I will provide you guys with an opportunity to ask questions regarding this study unit.